For the homework in this and subsequent chapters, we will make use of the thermodynamic data tables that can be found at the end of your book. Example of such a table is shown here for organic compounds at 298.15 Kelvin, and obviously 1 bar, since data is always given for standard conditions. At this stage, you can use these tables for information on the molar mass of a substance in gram per mole, its standard formation enthalpy, delta FH standard, in kilojoules per mole, its molar heat capacity at constant pressure, CPM, standard, and the standard combustion enthalpy, that is the standard reaction enthalpy for 1 mole of substance with the necessary number of moles of molecular oxygen gas to form CO2, water liquid, and if necessary, molecular nitrogen and sulfur dioxide. Note that as discussed in the preceding slide, the standard formation enthalpy of substances in their standard reference state is 0, as is shown here for carbon solid graphite. Here is another excerpt from the thermodynamic data tables found in the back of your book. Focusing on the element aluminum, you see that the standard reference state with 0 standard formation enthalpy for aluminum is aluminum solid. You can also see that the formation of aluminum gas is an endothermic process, since its standard formation enthalpy is positive. We will say that aluminum gas is an endothermic element. We also notice that aluminum chloride is an exothermic compound, since its formation enthalpy is negative. Exothermic formation reaction. Finally, note that these tables also allow you to estimate standard enthalpy changes at 298.15 Kelvin for fusion, crystallization, sublimation, vapor deposition, condensation, and vaporization processes. In the case of aluminum, for instance, the standard enthalpy change for fusion can be expressed in terms of the standard formation enthalpy for aluminum liquid and standard formation enthalpy for aluminum gas. In the last slide for this lecture, we will practice using the thermodynamic data tables to calculate the standard combustion enthalpy for glycine, for which an experimental value of minus 969 kilojoules per mole was obtained. First, we write the chemical reaction equation for the combustion of glycine with oxygen to form carbon dioxide gas, water, and nitrogen. CH2, NH2, COOH, solid, plus oxygen O2 gas to yield CO2 gas, plus H2O liquid, plus N2 gas. Note that we form nitrogen since glycine does contain the element nitrogen. The chemical formula of glycine contains 2 carbon atoms, so we form 2 moles of carbon dioxide. The glycine formula contains 5 hydrogen atoms, so we form 5½ moles of water liquid. There is 1 nitrogen on the reactant side, so there will be ½ mole of molecular nitrogen on the product side. Finally, there are 4 plus 5½ moles of oxygen on the product side and 2 moles of oxygen atoms in 1 mole of glycine, so we need 9¼ moles of molecular oxygen on the reactant side. We then use the reaction stoichiometry to express the combustion enthalpy in terms of the formation enthalpies of products and reactants. As a consequence, the standard combustion enthalpy of solid glycine must be equal to 2 times minus 393.51 kilojoules per mole plus 5½ times minus 285.83 kilojoules per mole minus 1 time minus 528.5 kilojoules per mole. We obtain delta CH standard for glycine as minus 973 kilojoules per mole, which differs only by 4 kilojoules per mole or 0.4% from the experimental value.